And we talked about bonding last time. We talked about polar bonds, non-polar bonds, using electronegativity to help us decide whether or not a bond is polar, which means there's sharing of electrons, but the electrons are being shared unequally. Non-polar, which means there's sharing of electrons, which means they are being shared equally. Or there's an ionic bond, which means there's no sharing of electrons, but we've had a transfer of electrons. Sort of our cutoffs when we use the difference in electronegativity, like we did in a couple, 0 to 0.4 is considered non-polar. Kind of above that to below 2 is considered polar. And again, kind of above 2 is considered ionic. Although, as we talked about, you don't really need the numbers for ionic bond. As soon as you see a metal and a non-metal, that's pretty much all you need, and it will be an ionic bond. You don't have to worry about any type of numbers or anything like that. I believe we started talking about drawing Lewis structures at the end there. And again, the steps that you want to follow to draw Lewis structures for covalently bonded guys. One of the first important things is to figure out the total number of valence electrons that's in the entire molecule. Remember that if you are drawing something that has a charge, you need to adjust your count so you get the right number of electrons. So if it is, wherever my thing went there. Yep. I was writing somewhere, I feel. There we go. There it is. If it has a positive charge, then you're going to subtract the number of electrons, and if it has a negative charge, you would add to your total. You want a logical arrangement, a skeletal sort of arrangement. Remember, it is the least electronegative atom that should be in the middle. Hydrogen shouldn't be in the middle. Once you do that, you want to make a single bond to the center atom. And that will use up a total number of electrons. Remember, each line is 2 electrons. Then you have some electrons left over. Those leftover electrons go as dots on the outside atom in pairs until each of the outside atoms have 8 electrons around them. Unless, of course, obviously it's hydrogen, then it shouldn't have any dots around it. If you fill up all the outside atoms, then at that point, you should then go to the center and put any leftover electrons at that point on the center, if you still have atom as pairs of dots as well. Last, you want to check to make sure everybody has met the octet rule. And it's really at that point, if they have not met the octet rule, that you should try to fix it by making a double bond or a triple bond, which I think is sort of what we finished up on. We drew carbonate, I think, there at the very end, if I'm not mistaken. And remember that when we make a double bond or a triple bond, we're not just adding electrons in, we're not just adding a double bond or a triple bond, but we're actually taking a pair of electrons and moving them in to make the double bond. So if you remember, I think the one we laid up on there was carbonate. And when we distributed all of our electrons, what we ended up doing was taking a pair of electrons, say from this oxygen, and bringing them in to make the double bond. The reason we want to do that is that will maintain the correct number of total electrons, and it will help complete the octet for everybody else there that was missing it. And again, typically put a little bracket and charge around it if it is something that has a charge. Any questions on those steps there? That was the last one we drew, yes? Yeah. I want to make sure I wasn't here alone. I just want to make sure. All right, so let's draw a few more just to make sure. So once you draw, let's do SO2. Why don't you draw, let's do CO2, let's do NO3 minus, and let us actually do N2. All right, draw the proper Lewis structures for each of these. See what you come up with here. Okay, let's take a look, see how we're doing. So once again, one of the first things you want to do is count up the number of valence electrons. So sulfur, there's group 6. There's 2 oxygens, also group 6. That looks like 18 valence electrons our picture should have. In this case, sulfur should go in the center as it is less electronegative than the oxygen. We're going to make one single bond from the center to the outside. That is 2 and 4 electrons. That leaves us 14 to go, I believe, if my math is right. So we're gonna go with pairs. So 2, 4, 6, 8, 10, 12. That fills up all the outside ones. I actually still have electrons to put on there, right? This is only 16 electrons. We do need to go to the central atom and put the dots on there. That is how they get there, by the way, and they should be there. That is now 18 valence electrons. Is everybody good here? No, the sulfur has only 6 electrons. It has 2, 4, and 6 around it. So we do need to make a double bond to fix it. You could actually do it from either oxygen. So we're going to take a pair of electrons and bring them in to make that bond. And that would get us something that looks like this. Or you could have done it on the other side, which would give you something that looks like this. And either one would have been perfectly fine. I think we might have talked about this last time, but these guys are what are known as resonance structures of each other. And basically they develop because there's more than one place where you could make a double bond. And those double bond electrons are what are referred to as being delocalized. They're just moving around. So at any given point, they may be to the oxygen on the left, maybe the guy on the right. You don't have to draw all the resonance structures unless it asks you to do so. So you can lay up either one of those pictures, would have been perfectly fine. The ones with the double bond, obviously, would be the correct ones there. Any questions on that one there? Yeah. I did. It's just typically when people make double bonds, they kind of double bond and then put the dots on the left and right hand side. But truthfully, it doesn't matter. As long as you take a pair, you can take any pair you like. Yeah. Other questions? Okay, let's look at CO2 here. CO2 is carbon. That's what they say. That's 4. 2 times 6 for oxygen. Like a 16, we'll go with. How's that? Once again, here we're going to go carbon in the middle as it is the least electronegative. We're going to do oxygens on either side. We're going to do, again, a single bond to each of them. That is 4 electrons. That means I got 12 more to go. We're going to go on the outside to fill them up. So that is 2, 4, 6, 8, 10. I'll go on this side of the line there. 12 at that point. At that point, I have now used up all 16 electrons. Is everybody okay here? No, our carbon is short. Our carbon has only 4 electrons, the 2 bonds. So we do need to try to fix it by making a double bond. So I'm going to take a pair of electrons and bring it in to do so. When I do, I end up with this. Did that fix the problem? It did not. It got us closer. We're now at 6 electrons for the carbon, but we do need to get to 8. So we wouldn't want to jump here to a triple bond because we still actually have an option to make another double bond, and we can make another double bond on the left-hand side there. So we would do the same thing here. Again, you kind of want to exhaust your double bonds before you jump to a triple bond, and we would bring those electrons in, double bonding the guy on the left as well. And now when we look at it, are we good now? We are. Everybody's got 8. We still have only 16 electrons. Any questions on that one there? Coming here to nitrogen, which is 5 plus 3 times 6. I'll put a parentheses there maybe. We also have a negative, which means we do need to add 1 to it. And that means 18, 19, 24 valence electrons. In this case, nitrogen will go in the center as it is the least electronegative. Oxygen's around. We'll do 1, 2, and 3 bonds. That is 6 valence electrons. Just have a lot more to go there. 18, I think. So that's going to be 2, 4, 6, 8, 10, 12, 14, 16, and 18 in this case. Once again, looking at our nitrogen in the center, it is short a pair of electrons there. So once again, here we could double bond at any of the oxygens you choose. So I'll take the guy from the top here, we'll bring it in. And when I do that, we end up with a double bond up on top. Our other guys stay single bonded. And really should put a bracket around it with a negative charge. You could draw two more resonance structures for that one where you double bonded to the left or double bonded to the right. Again, either one would have been perfectly fine. Any questions on that one there? And lastly here, our nitrogen, which would be 2 times 5. That looks like a 10. There really is no central atom here. There's just 2. So you could approach it the same way. Just put them across from each other. You'll do the same thing. You're going to connect one bond there. That is 2 electrons. That's 8 more to go. We'll distribute on the outside. So that is 2, 4, 6, and 8. That is all 10 electrons at this point. Nitrogen on the left is a little short. It's only got 4 electrons. So we'll try to fix it by making a double bond. We're going to bring those electrons in to do so, which will give us something that looks like this. Did it fix it in this case? It did not. Again, it got us closer. Nitrogen on the left now has 6. I got nowhere else to make a double bond, so now I need to make a triple bond to fix it. Works the exact same way. Once again, we're going to take a pair of electrons and move them in to make our triple bond. And now we will end up with nitrogen, and why it is triple bonded. Looks something like that. Each nitrogen now has, again, 8 valence electrons around it and only 10 total electrons. Question on how to draw Lewis structures here. So obviously you need to be able to draw them correctly. If you follow those steps, you will end up with a pretty good structure, probably the right structure. If you do not follow those steps, then you probably end up with not a great structure and maybe too many electrons, not the right number of bonds and stuff like that. This should really lead you to sort of a pretty good structure. Any questions on any steps? Yeah. We are coming up. Yep. All right. Okay, so let's continue talking about that, and we'll get to that when we talk about geometry and then into the polarity part in just a bit here. We talked about resonance structures. Again, a resonance structure is something that as you draw, you can have more than one place where you can basically make the double bond. So you have ways to kind of move it around. And you can draw equivalent structures because one really doesn't describe what's going on sort of correctly. But first, let's talk a little bit about bond length. You do not need to memorize any of these numbers, but when we look at, for example, a single bond versus a double bond versus a triple bond for carbon, 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 and carbon, what we see in terms of the bond length is single bonds 154, double bonds 133, and a triple bonds 120, the distance between the 2 atoms. Same thing happens with a single bond for carbon, nitrogen, 143, 138 for double bond, and 116 for a triple bond. What happens is as we make the double bond and triple bond, we bring the electrons in, it basically moves everybody in closer. So they get moved in closer and closer. So the single bond is sort of furthest away, bringing those electrons in to make the double bond brings everybody closer, and making the triple bond brings the distance between the 2 atoms much closer to each other. That obviously has a relationship on bond strength. A double bond is stronger than a single bond, and a triple bond is stronger than a double bond. They're not like twice as strong or 3 times as strong, but that's the general trend that you see. I equate it like a brand new pencil. We get a brand new pencil out of the box, nice and long, pretty easy to snap, right? You take a chemistry test and you're left with like a nubbin and an eraser, right? It's like that big. It's very, very hard to try to break that thing apart. And the same thing happens as everybody moves in. As you make double and triple bond, everybody's really, really tight to one another, which means all the interactions are really close to one another. And it makes it really hard to sort of break those guys apart. And you get a much stronger bond that occurs. So as I mentioned, resonance structures, as we drew a few there and last time as well, is really anytime you got an opportunity to basically double bond in more than one place. And for something like carbonate that we did the other day, the idea is those double bond electrons that we kind of bring in to make the double bond when we're drawing the Lewis structure, they're delocalized. So again, at any given point, they may be the guy on the left, but then they may move over there to the guy at the top, and they may be over there to the guy to the right. So any one of those three sort of resonance structures that you could draw with when you drew the Lewis structure could properly represent what's happening. The true structure is probably somewhere between all three of them. We usually put this sort of double-headed arrow between resonance structures to indicate that they are related to each other. So if you kind of see that arrow between two Lewis structures, that means that they're related to each other. And really probably the only thing that's different is they moved the double bond to all the possible locations when they drew it. So there was our carbonate example. And don't worry about the charges, but again, we could have double bonded up here, or we could have double bonded over here. And obviously we could have done a double bond over here. And again, they're all related to each other. If you're out to draw the Lewis structure, you don't need to, again, draw all of them. You just need to draw one of the three structures would be sufficient. Benzene ring is actually something that looks like this. It's 6 carbons and 6 hydrogens, and it's got 3 double bonds inside of it. And again, you can draw some equivalent structures that look something like this. These are all carbons at these points. We'll see benzene again when we talk about organic, but it's an organic compound. There's actually a hydrogen at each of these points. Also why sometimes you will see benzene drawn like this with a little circle in the middle to indicate that those double bond electrons could be pretty much anywhere, kind of moving around and stuff like that. We'll see benzene again later. All right, there are some exceptions to the octet rule, and let me be really clear here. We will never have any exceptions to the octet rule, but you should know the 3 exceptions. You'll never be asked to draw any of the exceptions, but you just need to know what those exceptions are. One exception to the octet rule is what's referred to as an incomplete octet, and that means that it has less than 8 valence electrons around it. For the most part, boron is pretty much the guy that does that the most. So as you can see here, boron actually only has 2, 4, 6 electrons around it, and it's perfectly happy with that. It doesn't need any more. Beryllium and aluminum does it, but they're really kind of metals, so they pretty much kind of really behave more ionically. So really boron is sort of the one that you sometimes will see it, not in here, but that is an exception to the octet rule. Other exceptions to the octet rule, and again, you will not be asked to draw any of these, nor should you draw anything that is an exception to the octet rule, because we're going to pretend it doesn't exist in here, but you should know them. It's an odd number of electrons. They're sometimes referred to as free radicals. So occasionally, sometimes somebody ends up with kind of an unpaired electron by itself. It's very popular in atmospheric chemistry with chlorine, because they actually have one unpaired electron. They're very, very reactive because they don't want to be that way. They want to kind of get another electron going. So they're very, very reactive sort of guys that are an odd number of electrons. The last one here, which is one that you should not do in here either, and that's why you shouldn't Google ask questions or anything like that, because they'll know you did it because you drew something you shouldn't, is an expanded octet. And expanded octet, there are actually elements starting at sulfur at the periodic table, to the right, to the left, and down. When you're doing covalent bonding, they have the ability to go over 8 electrons. So they could do an expanded octet. They could do upwards of 12 electrons around them, and they're perfectly fine doing so. That is because when we get to sulfur on the periodic table, that is period number 3. And period number 3 means that the energy level would be the 3rd energy level. And what orbitals are on the 3rd energy level? There are s orbitals, there are p orbitals, and on the 3rd energy level, that is where d orbitals begin. So these elements, although they may not be using them, have actually d orbitals available to them to allow them to go over 8. And that's why you'll sometimes see it drawn over 8. Once again, not in here, but they have the ability to do so. That also means that if you look on the periodic table where nitrogen, oxygen, carbon, and fluorine, that is period number 2 on the periodic table, which has only s and p orbitals, no d orbitals. and they should never, ever, ever go over 8 because they don't have the ability to do so. So the place that most people get in trouble is they Google sulfate and they draw this. Maybe you did earlier. Hopefully you didn't. And it looks like that, which is actually an okay structure for sulfate, but not in this class because you shouldn't be drawing anything that looks like that, by the way. So your sulfate should be all single bonded. So in case you have that on your paper, make sure you change it before you turn it in. All right, so you do need to know. Actually, that's a better structure for sulfate, but not in this class. So you should do single bonded. All right, so you should know the 3 exceptions, but once again, everything, let me say it one more time, everything will obey the octet rule in here. So everything should obey the octet rule. Nothing should go over the octet rule. Nothing will go under the octet rule. If you end up with a negative number, an odd number, again, odd number, again, with a negative number, you're wrong. But if you end up with an odd number, then you definitely added wrong in this class. But there are things, obviously, that could go more, and there are things that could go less. But just not here. Let's talk a little bit about geometry, and we're going to talk about molecular geometry of our molecules here. And we could kind of use really our Lewis structures, and more so how many electron pairs there are around the central atom to help us decide what the geometry is of the molecule. Most people have a very hard time sort of picturing things in 3-dimensional space, myself included. So the best thing on this is just memorization of the best way to do it is how many electron pairs and how many bonds, and it will correspond to a certain geometry is really sort of the best way to do it instead of trying to visualize sort of what's going on. We are going to talk about really 2 types of geometry, which I think you did in your lab. One's electron pair geometry, sometimes called, and one is the molecular geometry, which is sometimes referred to as the shape of the molecule. The electron pair geometry describes the 3-dimensional arrangement of all the electrons around the central atom. The molecular geometry describes the overall shape of the molecule as everybody moves. Because they're all sharing electrons, they're all locked together. As one thing moves, everybody else moves accordingly. Now, it's always about the central atom. So when you do geometry, it's all about the central atom. You don't care about really any other atom but that guy that's in the center. The basis of this idea is electrons basically don't like other electrons because they're negatively charged. So you get these negatively charged guys near each other that has to sort of coexist, but they really don't want to be near each other. So what ends up happening is they try to move away from each other as far as possible. They can't completely escape each other, otherwise everything falls apart. But as they move, like I said, the whole molecule will also start to move. As they kind of move one way, everybody else that's bonded will also move. And we end up getting some different geometries depending on how many electron pairs there are and how many bonds. And actually, we get different geometries or shapes depending on what type of electrons are present. What I mean by that is, are they bonding electrons? Are they non-bonding electrons near each other? So we get some different sort of shapes that occur based on that. This is what is referred to as VSEPR, or valence shell electron pair repulsion model. Probably why they abbreviate it. That's a mouthful. It's basically broken apart into 2 categories. One where there are no lone pairs or non-bonding electrons on the central atom. So pretty much when you draw your Lewis structure, no dots on that central atom. And there's ones where there are dots on the central atom, or non-bonding electron. Now, depending on whether or not there are dots or not around the central atom, it will affect what type of geometry that we do see. Really, the main important thing when you're doing geometry, and only when you're doing geometry, is any double bond or triple bond. It counts as 1 electron pair and 1 bond. So any double bond that you have in your Lewis structure, any triple bond that you have, when you go to count them, and again, only when you're doing geometry, you should count them as 1 electron pair and 1 bond. They are effectively moving as 1 unit, so they count as 1 electron pair and also 1 bond. All right, so let's take a look at some of these geometries here and how we could go about figuring them out. Let's start with the simplest geometry you could have, frankly, is a diatomic molecule. That means there's only two atoms involved. No matter what two atoms they are, the geometry is always going to be linear. The only way you could basically put two things is by a straight line. So you basically get a linear arrangement. That means it doesn't matter if it is single bonded. Doesn't matter if it's double bonded. Doesn't matter if it's triple bonded. Doesn't matter if it's the same element or different elements. It's linear, yeah. So as soon as you see only two and you need geometry, that's pretty much all you need to write is linear. It's always going to be a straight line. Doesn't matter, like I said, double bond, single bond, triple bond. Doesn't matter if it's the same two or different elements. If you only got two, straight line, basically ends of a straight line is how they can arrange each other, and it will always be linear. Any questions on that one? That's a pretty simple one. Let's talk about what happens when we get three or more atoms together. So let's take a look at this. Now, when we look at our Lewis structure, once again, we want to focus in on the central atom. So in this case, it would be the beryllium. And personally, this is the two things that I look for when I count and do geometry. I want to know the number of electron pairs. And those can be lines, they could be dots, it doesn't matter, the total number of electron pairs. In this case, the beryllium has 2 electron pairs, a bond on each side, right? One is each electron pair. The number of bonds there are is how many? Also 2 in this case, right? One on each side of the beryllium. Now, 2 electron pairs in terms of the electron pair geometry names. It is based on how many electron pairs there are. This is also going to be a linear geometry. Now, what happens is both of these pairs of electron are bonding electrons, which means the 2 Cl's decide, I don't want to be near you. I'm going this way. I'm going this way. And they end up ending up as far apart as possible, which is on opposite sides of each other. And the molecular geometry here are the shape is also going to be linear. It has a bond angle of 180 degrees from one side to the next, basically. Yeah. So something with 2 electron pairs, electron pair geometry is linear. Something with also 2 bonds, the molecular geometry or the shape will also be linear as well. Any questions on that one there? The next sort of example will be one where we have 3 electron pairs around the central atom. So if we look at this guy here, boron trifluoride, once again, looking at the central atom, number of electron pairs is going to be 3. All the bonds, each one is an electron pair. The number of bonds will also here be 3. So something with 3 electron pairs, the electron pair geometry name is going to be trigonal planar, or some people call it triangular. What happens in this case is we now have 3 things bonded. So the fluorines down here kind of go as far from that guy as possible, as far from that guy as possible, and also try to keep some distance between these two as well. So because we have that extra thing that is bonded there, they end up in this overall geometry shape. I'm just going to call it MG for molecular geometry. Is going to also be trigonal planar. It has a bond angle of 120 degrees. It is also sometimes called triangular because it makes a triangle. Yeah, so it makes an equilateral triangle, basically the shape of it. So that is why it's referred to as sometimes triangular in this case. So 3 electron pairs, once again, central atom you want to count, dots, lines, doesn't matter. And number of bonds here, 3 and 3, is trigonal planar for both the electron pair name and the molecular geometry name. Any questions on that? Again, a bond angle about 120 degrees there. The next example is a central atom where we actually have it messed up. It's a bad job there. Let me redraw that there a little bit better. I think it's okay on your picture, I think. Maybe. There we go. All right, so looking at our central atom here, the number of electron pairs is going to be 4. The number of bonds is also, in this case, going to be 4. Something with 4 electron pairs has an electron pair geometry name of tetrahedral and a molecular geometry name of tetrahedral as well. It ends up being a bond angle about 109.5. It kind of makes a triangle on the face and almost like a pyramidal type shape-ish on the bottom there. It's a tetrahedral sort of geometry. So 4 electron pairs around the central atom, 4 bonds, tetrahedral for both the electron pair geometry name and the molecular geometry name. Up until this point, has the names been different? Both of the names are exactly the same, and that is because the only type of electrons we have in this example, in the previous example, and in the previous example is they're all bonding electrons, which means the electron pairs around the central atom are all attached to the atoms themselves. So as those electron pairs move, so does the overall shape of the molecule moves exactly the same way. And whenever you draw a Lewis structure where there are no dots on the central atom, both the electron pair geometry name and the molecular geometry name will always be the same, because they're basically the only one type of electrons, and as they move, so does the atoms, and that gives you the overall shape's going to be the same. So they're always the same name when you have no dots on your central atom. It is only when we put dots on the central atom that we actually do get some different names, and the name that's affected is only the molecular geometry name. So it is only the molecular geometry name that gets effective when we introduce non-bonding electrons to the central atom, or dots to the central atom. So when we introduce those dots to the central atom, that is when we start to see some different names. The reason we see different names is when we have dots on the central atom, there's no atom that's actually bonded to it, right? So it has a little bit more room to move. And when it has a little bit more room to move, because they're just electrons, the overall shape of the molecule actually tweaks a little bit, and it ends up in a different shape than it does if you did have the extra atom still bonded there. The electron pair geometry name stays the same, so it's still based on how many dots or electrons you have around the central atom. Dots or lines around the central atom. The real reason is also we do get some interaction between different types of electrons. And frankly, the best case scenario in terms of electrons is what we were dealing with, like lines near lines. That's like an okay deal, bonding near bonding. The next worst situation is where we get some dots near lines, so non-bonding electrons near bonding electrons. That is like not so great. The worst case happens when we get non-bonding electrons near non-bonding electrons. They frankly want to go as far away as possible from each other. They're able to do that because they're not attached to an atom. So they're kind of free-ish, if you will. So they're able to move a little bit more. So again, as these non-bonding electrons really move out a little bit more, and there's a little bit more room, the overall shape of the molecule really starts to change. So let's take a look at an example here, sulfur trioxide. And let me draw it there, because apparently we did draw it earlier. Looks something like this. All right, when we look at the central atom here, how many electron pairs are there? Pairs, there would be. There is 1 electron pair, 2 electron pairs. Double bond counts as only 1. There's actually only 3 electron pairs around that sulfur. And that means that there are 3 electron pairs. Number of bonds would be in this case. Number of bonds would be 1 bond there, right? And again, the double bond only counts as a single bond as well. So there's only 2 in this case, yeah. Any questions on how we counted that there? Yeah. Remember, in geometry, double bond, triple bond, 1 electron pair it counts and 1 bond. Now, before we talked about something with 3 electron pairs, the electron pair geometry does not change. So something with 3 electron pairs is still trigonal planar. But now we're missing that 3rd bond that we had before. So we have this like non-bonding electron here, which gives it a little bit more room to kind of spread out. We also have non-bonding electrons near bonding electrons, which is not so great. They want to get away a little bit more from each other. So our molecular geometry ends up being, I personally go with angular. Some people go with bent angular. Some people go with just bent. Personally, I roll with angular for this particular one, and that is because of the bond angle. The bond angle is just less than 120. It is based off of this bond angle, which is 120 degrees. So it's just less than 120 degrees. So the 3 electron pairs that are there are still going to kind of go out into this sort of trigonal planar triangle type shape. But again, with that extra kind of movement that they can have without the 3rd bond, it allows those oxygens to get a little bit further away from each other, and it ends up being a more angular type of geometry than the trigonal planar geometry we saw in the previous one. Any questions on that one there? Next example will be something like NH3. NH3, when we look at the central atom, which is our nitrogen, the number of electron pairs is how many? Doesn't matter if they're lines or dots. How many? 4 is right. Yes, there are 3 lines and 2 dots. That is 4. The number of bonds would be 3. Yep. So once again, the electron pair geometry is based on the number of electron pairs. So our electron pair geometry here is going to be tetrahedral still. Once again, here we have this non-bonding electron. In the normal tetrahedral, we have an actual atom bonded up there. So they're not bonded. So this allows this electrons to get away from those non-bonding electrons. But again, they can't go too far with that extra hydrogen that's down there. And we end up with a molecular geometry known as trigonal pyramid, because it kind of makes like a triangle up on top and a pyramidal shape there on the bottom. Yeah. So our trigonal pyramid type shape has a bond angle of less than 109.5, which is the tetrahedral bond angle, just slightly less, again, with the extra non-bonding electrons, no atom there, able to kind of tweak a little bit more. This brings us a really good point of 2 names that we've just talked about here. And that is trigonal planar and trigonal pyramid. They are 2 different things. That's trigonal planar is 3 electron pairs and 3 bonds. Trigonal pyramid is this one, 4 electron pairs and 4 bonds. On an exam or something like that, you know, don't just write trigonal and let me choose because I failed chemistry. I'm going to choose wrong. I'm going to choose an X. Yes. Or my other favorite one, it is trigonal. I'm very confident. Planar, I'm still confident. Something like, clearly that is pyramid or whatever one it was supposed to be. So, you know, flip a coin if you're not sure, but hopefully you should be sure. But do not just write trigonal. You do need to specify planar or pyramid. They are 2 different shapes and they are 2 different bond angles that are happening there. Any questions on that one there? All right, the last geometry that you need to know is one like this here, like our friend water. And that is a central atom here of oxygen. Number of electron pairs is pairs. 4. I like it. That's good. That's 1, 2, 3, and 4. There we go. Number of bonds would be 2. Yeah, there you go. So once again, something with 4 electron pairs, the electron pair geometry name is still going to be tetrahedral, like all the other ones that we saw that had 4. But in this case, we actually have all the bad interactions happening at once. We have bonding electrons near bonding. We have non-bonding electrons near bonding. And then we have non-bonding electrons near non-bonding electrons, which really don't want to be near each other. So what ends up happening is these non-bonding electrons go this way, and then our hydrogens go the opposite way to get away from each other. And the result of this is we get a molecular geometry of bent or V-shaped, which is why I use angular for the other one. And the bond angle here is just less than 109.5. It's like a buck 104 or something in that ballpark. Best way to do it, like I said, is just number of electron pairs, number of bonds, and memorize what geometries go with it. Any questions on that there? For us in lecture, you only need to know the molecular geometry. You don't need to know the electron pair geometry. I went over it because I think it was in the lab, right? If I'm not mistaken. So usually it is. So for us in lecture, you just need to know the molecular geometry. So again, number of electron pairs, number of bonds, correct geometry that goes with that is probably the best way. Make a little table like the one that's in the book-ish, and you could kind of basically do that. All right, any questions on geometry? All right, so let's then talk about polarity. We talked about earlier a couple of things. We talked about bond polarity, and when we talk about bond polarity, that is using electronegativity values and basically the difference in electronegativity values to determine whether or not a bond is polar or non-polar. Now, there's really kind of one place only where bond polarity and molecular polarity cross over and are the same, and that is when we are dealing with diatomic molecules. So with diatomic molecules, bond polarity, where we use our difference in electronegativity, and molecular polarity are really one and the same. They basically come out the same. By the way, when we talk about molecular polarity, we're not talking about any individual bond. We're talking about the entire molecule as a whole. Is it sharing those electrons equally, or is it sharing it unequally? If it is sharing it unequally, the molecule will be a polar molecule, which means it has a positive side to the molecule and a negative side to the molecule. And it has what is referred to as a dipole moment. So if it is a polar molecule, it has a dipole moment. And that dipole moment is the same type of arrow that we use for our bond dipoles. You could draw it. It points to the more negative side of the molecule. This side is the more positive side of the molecule. If it is a nonpolar molecule, that means overall the molecule is sharing the electrons equally, and there really is no side that's more positive. There's no side that's more negative. It's kind of like a neutral molecule. It's just kind of no charge on it. It's like perfectly equal sharing of electrons. So with diatomic molecules, it's pretty simple to figure out. So if we took something like we saw before, like these two guys here. First off, this guy or this bond right here, is that a polar or non-polar bond? The electronegativity value of fluorine is 4. This fluorine would be 4. When I take the difference, it equals 0, which makes it what type of bond? Non-polar, right? So that's like perfect equal sharing of electrons. So this bond here is a non-polar bond based on difference in electronegativity values. And because that is the only bond in the entire molecule, then the molecule here has to also be a non-polar molecule. And that, again, it's just very simply, there's just one bond, and that one bond is non-polar, so the whole thing is going to be non-polar as well. How about this guy? That bond between these two are polar or non-polar? It is non-polar. So once again, this is a non-polar bond. And because that is the only bond in the entire molecule, this guy would be a non-polar molecule. How about this guy here, HF, polar or non-polar? That bond. So hydrogen is 2.1, fluorine is 4, difference is 1.9. Is it polar or non-polar? That is definitely over 0.4, yes, below 2. That is a polar bond. And because that is the only bond in the entire molecule, that means that this molecule will be a polar molecule, which means it has a dipole moment where it is actually heading in that direction, yeah, to the more negative side. That means the fluorine side is more negative in that molecule, the hydrogen side is more positive. So diatomic molecules are the simplest if it is a polar bond, and it's the only bond there, the molecule has to be polar. If it's a non-polar bond and that's the only bond there, it has to be a non-polar molecule. Any questions on diatomic molecules? Now, if everything worked that way, that'd be great, but it doesn't. So when we get to 3 or more atoms, we have to look at 2 things. We have to look at, are there polar bonds? And we have to look at the molecular geometry or the shape. So for example, if we did our bad drawing of CO2 like we did earlier there, try that again. All right, our CO2 does not want me to draw CO2. Let's try it over here, CO2, maybe it likes it better. There we go. All right, we draw our CO2. So we want to decide, are there polar bonds? Is the bond between carbon and oxygen polar or non-polar? What do you think? Carbon and oxygen are in the same period on the periodic table, yes. Which means electronegativity increases which way? Up and to the right, yes. That means they're in the same period. Should they be polar or non-polar? They should be polar, by the way. Yes, they're in the same period. One is further to the right, so it will make a polar bond. That means the oxygen is actually more electronegative. So if we were to draw the bond dipoles, it would look something like this, both pointing to the oxygen. So the answer for this one is yes, it has polar bonds. The geometry of CO2 is, what is the molecular geometry here? How many electron pairs here? The number of electron pairs is 2. Each double bond counts as only 1 electron pair, right? Number of bonds is 2 as well. Each one counts as only 1. Something with 2 electron pairs and 2 bonds, the molecular geometry is linear. Yes, straight line, like we just talked about. So we have something that is linear like this, and I have an oxygen that is pulling this way. But wait, I have an oxygen that is pulling this way. I am actually pulling on my pen. Is my pen going anywhere? It is not, yeah. So what happens in this particular case is, even though they have polar bonds, because of the geometry, they actually cancel each other out. And this molecule is actually non-polar, this molecule. And it's a good example that you could definitely have a molecule that has polar bonds, but because of the geometry, they may cancel each other out. That is because these things here are vectors. They have direction, they have magnitude, and that's all I remember from the class ahead of us, which is physics, I think. But in certain cases, I woke back up and I remembered that in certain cases, they cancel each other out like we just saw. And in other cases, they will actually add to each other. So let's take a look at water. Between hydrogen and oxygen, is that a polar bond? Yes, it is a polar bond, yes. So between hydrogen and oxygen, it is a polar bond, with oxygen being more electronegative. So we will have our guy going towards the oxygen. So once again here, water does have polar bonds. What is the geometry of water? We just did it. The molecular geometry here is going to be bent or V-shaped. Yeah. It has 4 electron pairs and 2 bonds around the oxygen. So that is 4 electron pairs and 2 bonds. In this particular case, the guys will actually add to each other. So if you think about it, it is basically bent or V-shaped like this. You got a polar bond coming this way, one coming this way, like you're grabbing from the top. If I took something from the top and just pulled it, right, you kind of imagine that the whole thing would move. And they actually add to each other, and we get a net dipole moment that is happening going this way, where the oxygen side of water is more negative, the hydrogen side of water is more positive, and this would be a polar molecule. By the way, how the vectors work is you draw one, and you take the other one, kind of put it head to tail, and then they add together in this case for a net dipole heading in that direction. In that direction right there. Yeah. All right, so who wants to draw those things? Nobody wants to draw those things. Nobody wants to do that stuff. Just want to ask somebody what it is, I think, right? So the good news is, in most cases, there are certain geometries which are symmetrical geometries, and there are certain geometries which are unsymmetrical geometries. And you can use that to probably very quickly answer the question, is the molecule polar or non-polar? So let's talk a little bit about symmetrical geometries. Symmetrical geometries, and these are molecular geometries, are things like, what do you got there? You got trigonal planar. You have tetrahedral, and again, these are the molecular geometries. I think that's all you got on that for you guys, I think. And what these two basically share in common is there are no dots on the central atom. And if you have that situation and all the outside atoms are the same, it is most likely going to be a non-polar molecule. And that is because they will essentially be symmetrical to each other, like two people pulling on a rope, equal and opposite of each other, like tug of war. Everybody's pulling equally, right? The flag doesn't go anywhere. So they kind of cancel out to each other. And that will give you basically a non-polar molecule. Like if you had something, there we go, like this. Between carbon and fluorine, or is that a polar bond? Yes, carbon and fluorine are still in the same row there, and fluorine is still further to the right, and fluorine is the most electronegative element you could have. So we actually, again, here have 4 polar bonds, but there are no dots on the central atom. These are all symmetrically opposites of each other. So basically you have 2 fluorines pulling this way, you got 2 pulling this way. They're going to cancel each other out, and it will end up being a non-polar molecule. So how vectors work is if you have vectors basically heading in opposite directions, they cancel each other out. They're heading right at each other, they cancel each other out, like 2 people pushing on a door equally. Door is not going to open. And if they're not heading right at each other or opposites of each other, then they will not cancel out, they'll actually add to each other. Now, what would happen if I took my same guy here with my fluorines without putting my dots on them, and I swap out a hydrogen for one of the fluorines in this case? I still have my polar bonds happening this way, right? Carbon-hydrogen bond is actually non-polar, so it has a difference of 0.4. So what happens in this case is I got 3 of these guys that are pulling this way, right? And my hydrogen on this side is actually pushing a little bit with them, going in that direction, believe it or not. So you can kind of visualize if everybody's kind of pushing in the same direction or pulling in the same direction, that whole thing is going to move. And now this thing that was non-polar to the left there, we now swapped out one of the elements, and it now becomes a polar molecule. So if you have one of those 2 geometries and everything is exactly the same element on the outside, it is a safe bet just to write non-polar molecule. you have one of those two geometries and everything on the outside is not the same element, it's probably a safe bet to write polar molecule. Any questions on that? Because you will get some unequal sharing of those electrons. Now, there are some unsymmetrical geometries. And basically what these unsymmetrical geometries are for you guys is trigonal pyramid, angular, and bent or V-shaped. What all these guys have in common is when you draw your Lewis structure, you got some dots on the central atom. And if you have dots on the central atom and all of the elements on the outside are the same, it is going to be a polar molecule. So if we take our water, for example, I see dots on my central atom. I see everybody on the outside is the same. This is going to be polar. So basically, if you draw your Lewis structure, you see dots and everything on the outside is the same, but it's a polar molecule. You'll be fine in most cases. If you draw your Lewis structure and you have no dots on the central atom and everything on the outside is the same, put non-polar, you'll be all right in most cases. And if you draw your Lewis structure, you have no dots on the central atom and everybody on the outside is a different element, or there is a different element on the outside, it will become polar. The only one you have to think about is linear, which is pretty simple because it's a straight line. So if you have the bond electronegativities going opposite like our CO2, they will cancel. If you have them both heading in the same direction, the electronegativity arrows, they will cancel. But it could be they all head in the same direction, all the arrows, then it would be a polar molecule. So linear is the only one you have to think about, but basically your option for linear would be they head in opposite directions, non-polar. They head in the same direction at each other, non-polar. Are they all head in the same direction, polar? So that would be to your linear options when you draw it there. Non-polar, non-polar, and then polar. Question on the quick way to do molecular polarity. So let's see how quick we could do it. Let me re-sketch some of the ones we did before. So earlier today, we drew this guy here. Ooh, very badly. We drew this. We drew this. We did that one. We did. I'll add a couple of extra ones here. We'll do this one. We'll do this one. All right. So first off, let's start with this one here. This is two guys together, right? Which means all we have to determine is the bond. Is that bond polar or non-polar? Between two nitrogens. It is non-polar, which means this molecule is non-polar. Here I see what on my central atom? Dots or no dots? Dots. Everything on the outside, same or different element? Same. So dots, same element, polar. Here I see dots or no dots on the central atom? No dots. Everything on the outside is the same, polar or non-polar? Non-polar. Yes, symmetrical geometry. Here I see dots on my central atom, outside atom, same or different? Same. So dots with same elements going to be polar. Here I see dots, elements on the outside are the same, polar or non-polar? Polar. I think we drew this one maybe at the very beginning. Polar or non-polar? That's going to be polar, right? Polar or non-polar? Non-polar, right? No dots, everybody's on the outside is the same. See how quick you could do it? Yes, don't think about it, just do that. Yeah. Any questions on that there? Okay. So I believe that is this, but we do have a couple of naming things to do. So give me 1 second here. All right, so we talked about type 1 and type 2 naming in discussion. Let's finish up talking about the naming part here. So type 3 compounds are basically a little bit different than type 1 and type 2. Type 1 and type 2 are ionic compounds. Type 3 compounds are guys that only contain nonmetals. So these are sharing of electrons. And type 3 guys are really the easiest to name, but they are also the ones that people screw up the most because they want to do all kinds of things they shouldn't do. So I don't think it's that table anymore. This is actually the place where you use prefixes. I know everybody wants to use prefixes when they're naming, but this is actually the place where you should use them. We actually don't have to worry about charges. We don't have to worry about balancing things. Frankly, all you have to do is figure out how many you have there and use the appropriate prefix. This is back in our notes at the beginning of the notes, I think. So this is prefixes like mono for 1, di for 2, tri for 3, tetra for 4, penta for 5, and so forth. We basically use the whole name of the first element that's present with the appropriate prefix if needed. And then the second name gets the appropriate prefix with the nonmetal, just like we did before, getting the IDE at the end of it. So prefix, whole name of the first metal, prefix, IDE, like everything else, kind of the second one. There are a couple rules. One rule is we never use mono on the first name, but it is okay to use it on the second name. And what happens sometimes with our prefixes is we can get a couple of vowels that back up to each other, like a couple of O's. So we typically get rid of the O on the prefix, an A and an O. We get rid of the A on the prefix. So like instead of monoxide, we call it monoxide. We drop one of the O's. So that is, again, a very common thing. 2 I's are okay, but an A and an O, not so good. You drop the O off of the prefix part of the name. So here's a table of our prefixes 1 through 8, along with nano, which is 9, and deca, which is 10, although we don't really get too much into that, but 9 and deca is 10. So tetra is 4, penta is 5, hexa is 6, hepta is 7, octa is 8. So let's talk a little bit about how we name these things here. And again, our couple of examples of things we do. If we had 4 oxygens, tetraoxide. Once again, here we would drop the A off of the prefix. And again, the mono, as I just said there, we drop one of the O's off of the prefix. Remember, again, something like H2O is water, NH3 is ammonia, and we go by those common names, not the dihydrogen monoxide. Yes, we don't want any of that stuff, or the nitrogen trihydride. All right. So why don't you take a second here and give the names of each of these, and let's do some formulas here. So we'll do dinitrogen trioxide. Let's do tetroxide. No. Let's do sulfur hexabromide. Let's do All right, so try names on the left there and formulas on the right. So once again, appropriate prefix, whole name of the first element, appropriate prefix, and IDE on the second element. Yes. Okay, so let's take a look, see how you're doing. So once again, these are probably the easiest ones to do, but really, like I said, people want to do all kinds of weird things and they kind of mess up on these. So you just need to keep it simple. First off, you need to identify what's there. So I see I, which is iodine, which is a non-metal. I see O, which is oxygen, which is a non-metal. That tells me I have two non-metals. That's a type 3, which means, frankly, all I need is some prefixes and I'm good to go. I have 2 iodines, so the prefix for 2 is di. And once again, we would use di and the whole name of the first element, which is iodine. The second one is there's 7 oxygens. The prefix for 7 is hepta. And the second element gets the IDE treatment like we did before. So it becomes oxide at the end. Here we would want to drop the A off of that prefix and go with heptoxide there. Again, the 2 I's are okay, but the AO or the OO is kind of the ones you have to watch out for. Any questions on that one there? Looking here, that's carbon, which is a non-metal. That's oxygen, which is a non-metal. Again, it tells you it's type 3. So rolling into our prefixes, there's just 1 carbon, which means the prefix is mono. Should I use it on the first name? I should not. So then I just use the whole element name, which would be carbon. Second one, there's 2 oxygens. The prefix for 2 is di, and the oxygen becomes oxide. So this is carbon dioxide. Any questions on that one there? I look at the last one there, which is P, which is phosphorus, which is a non-metal, Cl, which is chlorine, which is a non-metal. Again, that tells me it's type 3, so I'm rolling prefixes. Once again, I see I only have 1 phosphorus, so prefix for 1 is mono. And once again, we will not use it on the first name, so this is just going to be phosphorus. Prefix for 3 is tri, and our chlorine becomes chloride, like the second ending there. So this would be phosphorus trichloride. Yeah. Any questions on those names there? I think the easiest of all of them is actually what we see on the right there. I look at it and I see prefixes, which means that's all I need to know. Di means how many? And nitrogen is N, so I write N2. Tri is 3, oxide is oxygen, O3. Yeah, there's nothing to balance. You just frankly write what's there. Sulfur hexabromide. Once again, I don't see a prefix on the first name, but I do see it on the second. So that tells me it is a type 3. That means that the sulfur with no prefix, there's how many? It would just be 1, right? Because we don't use mono on the first name. So because there's no prefix, we could assume that there's just 1 and it's mono. Hexa is 6 and bromide is Br. So that would be Br6. Yeah, that would be that one. Lastly, pentaoxygen heptachloride. This made up thing. Penta is 5, oxygen is O, so that's O5. Hepta is 7, chloride is Cl. Looks something like that, yeah. Any questions on any of those there? So again, these type 3 are really the easiest. You basically just need to use the appropriate prefix. Remember the couple important rules, which is no mono on the first name. But once again, you can use it on the second name. So it's okay to use it on the second name. And again, the sort of double vowel situation that occurs. Any questions on that there? All right. So here's a review of the different types of guys we talked about. Type 1, which are ionic compounds. Those are with metals that have fixed positive charge. No Roman numerals or anything for those guys. Type 2 are with the metals that have variable charges. So you do need a Roman numeral. And type 3, like we just talked about, are non-metal, no charges or anything like that, but prefixes. As we probably talked about before, you should never ever probably mix Roman numerals prefixes because you're probably doing something incorrect. They all have their place. prefixes, Roman numerals, neither, basically. Yeah, on those. All right, so just to finish up here, polyatomic ions are basically groups of nonmetals that are actually covalently bonded together, but they actually do have an overall charge, so they are ions. This guy right here, which is NH4 plus, and that NO3 is actually NO3 minus. These are two polyatomic ions. The one nitrogen, the four hydrogens all have a +1 charge. Now that we talked about bonding, it is actually this guy here that is covalently bonded together, but ends up having an overall charge. So it basically acts as a cation. This guy here we drew as well, covalently bonded together and sharing of electrons like so. Has an overall charge of -1 and really acts as the anion in this case. So polyatomic ions are for the most part going to be pretty much like ionic compounds, type 1 or type 2. In this case, overall, we're putting together +1 and -1. So like we talked about before, we just need one of each of them, which is how we get to this overall formula of one of each of them. No charge in the formula, but it's actually two things that do have charges. Each of these have a special name. This is what is known as the ammonium ion, not to be confused with ammonia, which is NH3, no charge. So this guy is NH4 plus, which is ammonium. This is the nitrate ion. And actually, when we put them together, this thing here is known as the whole name of each, which is ammonium nitrate. So we just put the whole name together of each of those. So with polyatomic ions, they have formulas and they have specific charges to go with them, and they have specific names. So you need to memorize the names of the formulas and the charges. It will allow you to put things together correctly and actually know what the names are. For the most part, the only polyatomic ion that is positive, or one of the few ones that are positive polyatomic ion, is this guy, which means 9 times out of 10, the polyatomic ion that you will be dealing with will actually be negative, and it will be attached to a metal. And you would follow the same rules as you did for type 1 and type 2. The metal, again, is always the most important thing when it's there. If the metals in group 1, 2, or 3 are silver, lead, or silver, cadmium, or zinc, you do not need a Roman numeral. If it is anybody's a transition metal with a polyatomic ion, you would need a Roman numeral. So here's a table from your book of some of these guys, and there are some patterns at which you can sort of think about these things. Most of the time, there are guys that are related to each other. So NO3 minus, which is nitrate, NO2 minus, which is nitrite, SO4 2 minus, which is sulfate, SO3 2 minus, which is sulfite. The one with the most oxygens in a group of 2 ends in 8. The one with the least number of oxygens ends in ite. So they're all related to each other. They all have -1 charge. In the case of nitrate and nitrite, they all have -2 charge in sulfate and sulfite. The only difference is the number of oxygens. So when you have the most oxygens, you can think like you ate too much. Yes, you have the most oxygens is a good way to remember that. Ite for the least. Some people will remember all the 8s and know that if you needed an ite, it's just 1 oxygen less. Everything else is the same. Yeah. Or remember all the ites. And if you need an 8, it's 1 more oxygen. Everything else stays the same, the charges. There are some that are like 4 that are related to each other, like these guys. And these 4 are related to each other by just the number of oxygens. So the one with the most oxygens in a group of 4 that's related to each other, in addition to ending in 8, actually will start with per. So that is known as perchlorate. ClO3 minus is just chlorate. They both end in ATE because they have the most oxygens in that 4 group. ClO2 minus is chlorite, and the one with the least number of oxygens in a group of 4 will start with hypo. So that is hypochlorite, ITE. Other things that happen is sometimes you put an H plus in front of one of these guys, and you put an H plus, which is hydrogen. So you, instead of carbonate, you put an H in front of it, it becomes hydrogen carbonate and so forth. So these guys are negatively charged. They oftentimes will hook up with a metal, which means you really should follow type 1 or type 2 naming. You basically would name the metal either with or without a Roman numeral, depending on if it's type 1 or type 2. And for the polyatomic ion, you simply just use the name, no matter how many you have of them. So just to give an example to finish up on here, FeNO3 2. This is iron, which is a metal. That's NO3, which is nitrate. This is basically iron, which is a transition metal. I'm not sure what the charge is. You would do the same thing we did before. I have 2 of these nitrates. Each is -1, which means the overall negative charge is -2. The iron should then be what charge? +2 to balance it out, just like normal, right? Whenever you take a positive, negative guy, you need to equal 0. This then would be iron Roman numeral 2 because of the charge. And that would be nitrate. I don't care. It has 2 of these guys. It has no effect on the name for a polyatomic ion, much like, Cl2 doesn't affect the name when we do it with chloride. You do need to put parentheses around polyatomic ions if you have more than one. So you got to lay up some parentheses around them if you have more than one of them. As opposed to this guy, which would be NaNO3. What would the name of this one then be? Na is, do I need a Roman numeral? Sodium. I do not. It is fixed. So this would then be sodium, and the whole name of this guy is nitrate. That would be sodium nitrate. Yeah. So 9 times out of 10, your polyatomic ion is going to be hooked up with a positive metal. You basically just follow type 1 and type 2 rules. Either it means you need a Roman numeral or not a Roman numeral for the metal, and you use the entire name of the polyatomic ion. All right, we are out of time. Sorry about that.